Hello, everybody. My name is Nina,
And my name is Benny.
and we are both senior data scientists at Combient. And we are here. Um,
Oh.
What's that? Oh, okay. We are here to talk about the solution for wound treatment we did together with Mölnlycke Healthcare. But first, we are secretly launching Combient Mix. So I want to spend just 1 minute to explain what Combient Mix is, so you all know. So Combient Mix is a data science and analytics company. We are a fast-growing, highly skilled tech team, currently 25 people with 11 different nationalities. And backed by 28 big companies, we are committed to solve complex problems across industries. To give you some context, Combient is the leading cross-industry collaboration network in the Nordics, focusing on different key areas of business transformation to create competitive advantages for all. And data science is one of those key areas, and hence Combient Mix. So MIX stands for Machine Intelligence X. And the X is the most important letter in the mix. It's about being in the intersection of the industry, companies, and technologies. The X also stands for experience. It's about the companies getting a good experience with AI, understanding it, and implementing it successfully. And it's the value extractor. And it also it also represents the multiplier to a more holistic approach. And in short, we want to go beyond the AI hype. But now we would like to present you in detail the Mölnlycke TissueAnalytics case, where we developed a recommender system for wound treatment. So Mölnlycke Healthcare is a leading medical solutions company. They are producing wound care products and have their headquarters here in Gothenburg. TissueAnalytics is a Baltimore-based digital wound imaging platform that records, tracks, and analyzes patient wounds. It is used in hospitals across the United States, where healthcare professionals, instead of guesstimating wound parameters like the area, tissue composition, perimeter, and depth, they just take a picture with their smartphone. And the TissueAnalytics app then derives these wound parameters automatically from the images. In January 2018, Mölnlycke Healthcare joined a partnership with TissueAnalytics. And the purpose of this partnership is to simplify, standardize, and improve wound assessment. And we at Combient were asked to do a proof of value with the data that TissueAnalytics collected that far. So during a period of 2 months last year, we explored that data, we evaluated what can be done with it, and how data collection can be improved. So the data we got from TissueAnalytics, that was essentially a table with the key wound features as derived from the images. So that are wound colors and areas, length, width, and depth. And it also contained anonymized identifiers for the patients, facilities, and wounds. We got the dates of the visits and the year of birth of the patients. And then the app also allows that the healthcare professionals enter some optional information manually. That is the etiology, which is the underlying cause of the wound. So that could be, for example, a surgical wound or a diabetic ulcer or a pressure ulcer. And this can be selected from a drop-down menu, so that information is structured. And then there is also a field for the wound dressings, so how the wounds were treated. And that is a free text field. So for the data cleaning, pre-processing, data exploration, and feature engineering, we used PySpark and Scala on Databricks. And this is some summary statistics of the data. So the data was collected between mid-2015 and beginning of 2018. At the beginning, only one hospital in the US was using the TissueAnalytics app, but then in 2018, it was already 65 hospitals. The data consisted of around 70,000 observations of wounds for 20,000 wounds. So that means each wound was on average examined 3.5 times approximately. And these wounds belong to almost 8,000 patients. So each patient had on average like 2.5 wounds. These wounds are mostly of chronic nature or are caused by an underlying chronic condition like diabetes, for example. The percentage of wounds that had been seen by a doctor or a nurse is 56%. And the time between the visits is distributed like this. So the visits have, in most cases, been scheduled to be exactly 1 or 2 or 3 weeks later. Then only 25% of the wounds have dressing information, so information how it was treated. And while 75% of the hospitals do enter this information, it seems that those hospitals who treat the largest number of wounds don't have the time to do that. So.
Okay. So the goal is to build a recommender system. But in order to build a recommender system, you need some way to measure the efficacy of a treatment. And to do that, we need to somehow measure the growth of a wound or the sort of the shrinkage of the wound. And also, many wounds, I mean, they have different sizes. And you want to sort of be able to compare a small wound and a large wound in some way. And so that's sort of the problem that we're having here. How can we do this? So we make first an assumption. And the assumption is that the healing of a wound depends only on the current state and treatment. So once you have removed the previous sort of dressing, and you look at the wound, and you're like, okay, this state will now determine how it responds to the treatment I'm going to do. Of course, there's going to be a dependency on, I mean, the previous treatment, I mean, what kind of treatment they will do, but actual wound will not see that. So it will only depend on that's the assumption anyway. So the first idea we had, how do you get the laser? You know?
Yeah, here.
Oh, it's the big one. Oh, fantastic. So the first idea we had was essentially measuring the velocity of the wound edge. So it looks like this. So this is your wound. And we're measuring this sort of speed in this direction. And that was sort of the first idea we had. And then we looked at, tried to sort of prove that this was the case, or maybe it's not the case. But in fact, the data that when we plotted it, you see that the derivative of the area with respect to time actually goes basically like the area itself. So in order to make something size independent, you have to consider this ratio. So this is the derivative of the area with respect to time, and then you divide by the area, and then you get something which is hopefully not depending on size anymore. But this is actually exactly the derivative of the logarithm. So if this is now constant, it means that you have a very specific formula for how the wound decreases, because it's going to go exponentially. So e to the minus, and then there's a constant times the time. But of course, in real life, we don't have a continuous measurement of the size. We only have different, so you observe it maybe a week later. So the way we define this derivative is by this discrete form, which just looks like this. So, and the reason you do this is just because this expression is a bit hard to choose where to evaluate A when you do this, right? Because it's a discrete form. So, how does this relate to anything that they've been doing in research before? Well, actually, if you look at research trying to figure out how wounds heal, they have proposed different ways of measuring it. And they always use small size data to validate. And this is because they actually take animals and they cut small wounds in them and see how they heal. And of course, you're not going to do more than like 20 different. So it's very hard for you to get some information because the wound healing process is extremely noisy. And by extremely, I mean extremely noisy. So one popular metric that you can see if you look at in literature is defined like this one. So it's just, this is the discrete derivative of the area with respect to time. This is the perimeter. So this would be very similar to measuring the velocity of the edge of the wound. So this has a unit of centimeters per day. So we can ask ourselves which one is better. So we can take a look at this plot. So this is the one that was proposed in the literature, which they validated on 20 different animals. And this is our metric. So this is now plotted. So now you have the proposed score here. You have the size of the wound here. And you want this to be independent of size. This is not very independent of size. This one is a bit depending on size. The linear correlation is about 0.02. It is significant, but what does this bias come from? It's hard to tell. It could be that the nurses that treat wounds actually treat larger wounds differently than they treat smaller wounds and so on. But it's small enough to be happy that this is a very simple way to describe the healing of a wound. Okay, so we can look at the healing score with respect to different etiologies. So this is the diabetic ulcer. So it's the source of the wound comes from that the person has diabetes and they've probably been laying a lot. So there's sort of like a pressure wound. And here you can see the distribution of the healing score. So negative means that the size of the wound decreases. Positive means that it's increasing, so that's bad. And you can see that the process is in general extremely noisy because it goes quite a lot on both ways. And in general, some of these wound types are harder to heal than others, and some of these are quite much to the left, essentially. So surgical wound is about the nicest type of wound you can have because it means that you don't really have any underlying disease. But let's see, these pressure ulcers are quite nasty, actually. Especially stage 4, it means that there's a deep tissue damage. So it's really, really damaged tissue. Okay, so the healing rate actually turns out that it relates to the healing of the wound and sort of the status of the wound bed. So how much blood is flowing there, what is the metabolic rate, and these kind of things. So if you can estimate the healing rate for a certain individual, then you can make a pretty good guess of how long it will take to heal. And also, what this kind of healing score provides is that you can actually start to try and doing A/B tests or tests for different treatments, because now you have a size-independent way of measuring the efficacy of the treatment. So one thing which is sort of gut feeling is that compression treatment works for many wounds. So you can say, okay, maybe it makes no difference. That's a null hypothesis. And then you can try 6 different etiologies. That's what we did. We chose the ones that were, well, they were chosen by my wife, actually. She's a nurse. She said, these are the ones that are probably going to work, and these are the ones it's not going to work. And the ones that it didn't work for, I think we got a p-value of 10 to the minus 195 or something like that. So, I mean, it's nice. And also, time to next visit, you can sort of measure, does it make a difference if you wait 4 weeks until you come back to the doctor and get a reapplying of the treatment, or if it's less. So we did a test for 1 versus 2, 2 versus 3, 3 versus 4, and actually this one, they're ordered actually. It's quite interesting. This is actually the best one, and that's the second best one, and so on. Yeah.
Okay, so the next question we were asking ourselves was, can we recommend wound treatments based on wound characteristics? So for this, we use the technique of collaborative filtering, which is often used when it comes to, for example, movie recommender systems. So if you assume that, for example, Benny and I have approximately the same movie taste, and we rate a number of movies equally good and bad, and then I go and watch a new movie that I really like, then it is much more likely that Benny also likes that particular movie and not some other movie that the randomly chosen person really likes. And this can be translated to, well, whether wound dressing, or how good a wound dressing is at supporting wound healing. So the requirements we had for such a recommender system were, well, it should support the healthcare professionals and not replace them. So it should work like a search engine and produce ranked list of wound dressings, where the ranking is depends on how good, how efficient the treatment is. And then the recommender should also be good at giving new effective suggestions. And we used the ranking factorization recommender from To Recreate, which is an easy-to-use machine learning pipeline. So the ranking factorization recommender needs as input, well, users, items, and ratings. And one can also add like some other features that describe the user and item profiles. So as a user, well, we would use the wounds, right? But then, well, each wound treatment is independent. So, well, how good it works is independent of the history of the wound, right? So, essentially what this means is that each observation we have would be independent. So each observation would be a separate user. But then we only have one observation per user, and then the collaborative filtering doesn't work. So we need to solve that problem somehow. Then we need items that are recommended, and that would be the wound dressings. But if you remember, that was a free text field, so we have all the problems that are connected to people entering free text somewhere. So we probably have to categorize that information somehow. And then the ratings, that should tell us something about, well, did the wound get better or worse? So for the wound healing, we followed what is commonly done for like movie or book reviews. We developed a star rating scheme. So we said that, well, if the healing score is positive or the wound is getting bigger, that is bad. And if the healing score is negative or the wound is getting smaller, that is good. And then we had also to add the color information. So black, we assumed that black, which is necrotic or dead tissue, that this is worse than yellow tissue, which is a sign of a bacterial infection, and that is worse than a wound where neither black nor yellow tissue are present. Then for the wound dressings, well, after we did a basic cleaning of the text data, we got 431 different wound dressings. But many of these are kind of redundant because people write different things but mean the same. For example, for foam dressings, the nurse or doctor might write just foam or foam dressing or foam and the size of the dressing or just the product name or many different possibilities. So what we did is we used the wound care database with product names, categories, and description of the product. And then we matched the dressing description in our data to the categories in that database. And then we went over the results manually and did corrections when needed. And that we sent then to an expert for review. So at the end, we had 33 product categories, which were used as items in the recommender. So then we had the problems with the users, so that each observation is independent. If we use only one observation per user, the recommender doesn't really work. But so one option would be, for example, to say that, okay, let's say that all diabetic ulcers are one user. So we could use the etiology to separate the users, right? But then, well, we would suddenly have lots of observations for one user, and we only have 25 different categories, so we would have too few users. And also, well, diabetic ulcers, for example, can differ quite substantially in color, for example, or the age of the patient, or other parameters. So we also didn't really want to do that. So what we then tried was to do a hierarchical clustering for each etiology by age, size, and color. And that worked surprisingly well, and is a good compromise between specificity and generalizability. So this is how the recommender then should work. So the healthcare professional is taking a picture with a smartphone of the wound. Then the wound parameters are fed into a classifier. The classifier predicts to which user cluster this wound belongs, and then the ranking factorization recommender that has learned the hidden user and item profiles based on the historical efficacy and user similarity, then produces a ranked list of recommended treatments together with the predicted efficacy.
Okay, so we have only 2 minutes, but we'll cover some of the interesting aspects of evaluating a recommender system. So in general, evaluating a recommender system is actually very hard because what is actually train and what is test in this case, because if your test set is users that you have not seen before, then you have no information about those users. And if you sort of try to split them somehow, it's kind of hard to know what would be the correct way of doing a train and test. Actually, the true test would be to run it live, so you just train it on the full data set, and then you would do some kind of clinical trial to see if this is actually a good thing or a bad thing. Of course, that's not very... I mean, if you do a proof of concept, this is not something you would like to spend money on. And also, how do you actually measure the performance of a ranking? Like, it gives you a set of recommendations, so how do you measure that? So let's start with how you do with train and test. So the normal way of doing train and test in recommendation systems is to sort of take some of the items for each user and put them in the test set and use the other items as the training set. And then the goal is to, for each user, recommend only things that you have not seen for that user. So in this case, well, those both liked antimicrobials, and this one liked cellular and tissue-based, and so for user 1, you would recommend that one, and the test set is that one. So we did good. So how do you measure this? Well, you measure, one way to measure it is mean reciprocal rank. So you make a set of recommendations for each user, and then you say, oh, when is the first one that actually worked? And then you take 1 over that, so that's 1/3. And the dressing recommender gets 0.81 for us. So it's sometimes it's extremely good, sometimes it's very bad, but in general it's quite good. And this is how it would look like if you would run it. So you just input the etiology, the different areas of total, yellow, black, the age, and then you get a set of dressings, and then you get a predicted score as well. This would be the 5-star score, so 3.45. And you can change them to have different types of wounds and sizes, and you get different recommendations. And that's it. Yeah. Thank you for your attention.
Thank you so much. And are there any questions from the audience?
First of all, a great presentation. I have one question. Like you are taking an image of a wound, right? So if in case it is a zoomed in image of a wound, then how you are going to categorize what will be the area so that you can do the processing post?
Yeah, so what was the setup for this problem was that Mölnlycke had this data that they got from TissueAnalytics. And TissueAnalytics, they do the image analysis. And they didn't want to redo what TissueAnalytics had done, so we didn't get any images. We got the output from TissueAnalytics, which was the size of the wound and the sort of the width and height and the depth and different colors. That's all we got, so okay. I don't know about the images.
Sure.
Any other questions? I have a question about, since this is actually used for patients and by doctors, usually you have some kind of explainability. A patient might want to know why they're doing something, or they don't feel like it's working. They want an explanation, and machine learning in general is not the best at that. How do you tackle that problem?
Well, of course, it's not really our issue. That would be Mölnlycke's issue to get FDA approval for something like this. But in general, if you do a clinical trial and test this recommender system, and you would see that certain things work well, you could use that as a learning, and then, you don't have to explain why something works well if it works well in a clinical trial. So I don't know.
Thanks to Nina and Benny.